Welcome back to my tutorial series in PyTorch. Today we're going to be training a neural network model on the MNIST dataset. This dataset consists of images of digits, so someone drawing a 1 or a 2 or a 3, for example, and corresponding labels, so the actual value of 1, 2, 3. And the goal of the neural network is to look at an image of a hand-drawn digit and predict what digit that actually is. As we'll see in this video, the neural network architecture, although very simple, is able to make these predictions very well. In this video, we'll look especially at the data set and data loader classes of PyTorch. These are the two most important classes that you'll be dealing with if you decide to use PyTorch as a machine learning framework. If you're enjoying this tutorial series so far, please be sure to like and subscribe. There'll be plenty more videos in the future. Also join the Discord server. There's a link in the description to that, and enjoy. So for packages today, we're going to be importing PyTorch, of course, the neural network module of PyTorch, the stochastic gradient descent optimizer. This functional will be used as a one-hot encoder. I'll describe what that means later in the video. We have the dataset and data loader. These are like very important objects in PyTorch when you're dealing with any dataset really. Torch Vision, NumPy, and Matplotlib. So if you're following along with this tutorial series, we finished the last video by defining what a general sequential neural network could be expressed as. F of x equals this, it's kappa, I equals 1 to n, of Ri, Ai, x plus Bi, where this kappa notation here of functions Fi of x is just Fn of Fn minus 1 of F blah, 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 all the way up to F1 of x. So you take F1 of x, then you plug that into F2. Take the result of that, plug it into F3. Take the result of that, plug it into F4, and you do it over and over again. This AI is just a matrix, x is your input vector, and Bi is a bias vector. Your Ri's are the activation function that you're using in your sequential neural network. This is essential because if you didn't have your activation function, this sequence of linear transformations is equivalent to just a single linear transformation. And that's not a very powerful function when it comes to fitting data. So in this video, we're going to train using an actual proper data set. And so I have a data set here that I downloaded from this website. It's the MNIST data set. It's one of the most popular data sets to deal with when you're just learning machine learning. So my path is specified here. This is on my own computer, but of course, when you download it, you'll have your own path. And you'll need to unzip this file and there'll be process data, and then I'm looking at the training data here. And so I can load this into my independent data. These are going to be images, and Y, which are the labels for these corresponding images. So let's look at what exactly this is. And I need to import my packages. So if I look at X, it's a tensor. And this is usually the first thing you do when you open data. You look at something like this, and it looks complicated, and you might not know what it is. So the first thing I always do when I open something up is I look at the shape of it. So I'm 60,000 28 by 28. So it turns out that I'm dealing with 28 by 28 images, right? It's just a 2D image, and I have 60,000 of them. So for example, if I want to index this, x2 is just the third image. And if I look at the shape of this, this is going to be 28 by 28. And it's, of course, a torch.tensor. I can convert it to NumPy by doing .npy or .numpy. And if I type properly, I now have a NumPy array of this pixels in this image. And here I plot it below. I do plot.imshow x2.numpy. And I can plot it. And of course, it looks like the number 4. And my Y, which are my labels. So if I look at y.shape and x.shape, there's 60,000 images. Each are 28 by 28. And there is 60,000 labels corresponding to those images. So if I look at Y, it says that my first image is a 5, my second is a 0, and my third is a 4. We're looking at the third image, which of course is a 4. So I'm looking at, I plot the image here, plot.imshow x2.numpy, and when I give it the title, I go y2.numpy. So y2 is going to be the label corresponding to this image, and I want the actual value, so I go .numpy, and it gives me the value 4. So before we get into actually training on this data set, I want to talk about the one-hot encoder. So suppose I have some labels that look like this, and this is of course what my data set looks like. And if I look at y original, it might be like the first image is a 2, then a 4, then a 3, then a 0, then a 1. And when it comes to training on this data set, what's really convenient when you're dealing with classification tasks is to encode it in a certain way. For example, the fact that this is a 2 has no bearing that it has like a magnitude of the number 2. Or a drawn 4, this doesn't have to really do with a magnitude of the number 4. It's not like this is greater than this. So what you can do is you can encode it in a format where you're dealing with separate classes per se. So here I have my labels like this, but of course this doesn't mean that this is greater than this, like a number is. It's just a different class. It's just something different. So we can encode it. So what you do if you encode something like this, so here I have my data that looks like this, and if I call the one hot, so this is a one hot encoder on the y original, which looks like this, I get something like this. And this is quite a bit better, as it turns out. It determines that there's 5 different possible numbers that there is. There's 0, 1, 2, 3, 4. And so this 2 corresponds to the second class here. It's just like almost like a binary representation. The 4 corresponds to being the last class. So each of these numbers gets turned into a vector, where the 1 is in the location of what class that is. So it's like each class is its own unit vector, and there are 5 independent things that it can take. So this is like a unit vector pointing in whatever direction this is. The 4 is a different unit vector. And then there's no concept of one thing being greater than another, like 4 being greater than 2. It's just different unit vectors. They're just pointing in different directions, essentially. That's a way that you could think about it. And so I've converted my data set, which are labels, 2, 4, 3, 0, 1, which would be like the labels of these numbers, into different unit vectors. The main reason I'm doing this, you might wonder, why the heck are you doing this, is that these unit vectors will then be used in a very convenient loss function known as the cross entropy loss function. So here I have my y original. Y new is my one hot encoded version of y original. And so my 2 gets turned into this vector, 4 gets turned into this vector, and so on and so on. And so we can do this for the entire data set. So remember, my data set looks like this. It's just a bunch of labels, and the shape of it is I have 60,000 different numbers. Now, if I turn each of these numbers into its own vector, now I have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So there's 10 different numbers that y can be. So I specify that there are 10 different classes. I define y new here. And if I look at the shape of this, it turns each one of these numbers from y, which is just like, for example, here a 5, it will turn that into a vector. So if I actually look at y new, it says that the first class is 0, 0, 0, 0, 0, and it will probably fill a 5 in the middle. While the second number, which is a 0, that corresponds to the first class. So it's like a 10-dimensional vector, because there's 10 different classes it can take, and it is the first unit vector here, this image here. And so on and so forth. The other thing you could think about it like this as is the probability that an image corresponds to a certain class, or the known probability. So I know with 100% certainty that this first image corresponds to a 0 because I was told that it corresponds to a 0. And it's like that for every single number. So you can think of each one of these vectors as a probability mass function for each of the 10 different classes it can take. And so these are probability mass functions. And when we train our neural network, it's also going to predict probability mass functions. Only they're not going to be all 0s and 1s. It might give like a certain percentage of it belonging to a certain class. And we want those predicted probability mass functions for each data point to correspond as close to possible as this probability mass function. So there are also issues with the images as well. And of course, if I look at my x.shape, I have 60,000 images of 28 by 28. But if I want to use this in the linear transformation that I've defined above, the input things x need to be a vector. And this is pretty easy to turn this into a vector. What I do is I want to turn these images that are 28 by 28 into a vector, which will have length 28 squared. I just basically take the image, which is 28 by 28, and I sort of string it out into a vector. So there'll be 784 different free parameters or pixels in a 28 by 28 image. And so it's easy to change by using the view property. So here I'm going to resize it into, well, -1 says keep the 60,000, and then 28 squared, it's going to take this last axis and it's going to sort of turn that into a single vector. And I can use the .view function. Remember that x is a tensor. I use x.view, which is a property of a torch tensor. So it says keep the 60,000 here and then resize this 28 by 28 into a 784. And now I have 60,000 images. Well, they're not images anymore, they're vectors, right? Which contains all the information about the image. And it sort of squishes this 28 by 28 thing into a vector of length 784. So we've gone over how to modify y and x. These will be used below. And now we're getting into the PyTorch data set object. This is such an important class in PyTorch. So data set is simply just a class in PyTorch, right? It's an abstract class. And the idea is that you use object-oriented programming. I have a tutorial on object-oriented programming. I'll put a link in the description to that. But you use the functionality of parent and child classes to inherit from this data set in your own data set class. So what you need to do first is you need to define an initialization function. So what this initialization function does in my data set is that it takes in a file path. And the file path is where the data is stored. So this is where it's stored on my computer. You can see I'm initializing it here. And what you do is you first load the data from that file path, sort of like I did above. So here I loaded the data from the file path. That's what I'm doing in this function. Well, the images go from 0 to 255, the pixel intensities. I want them between 0 and 1. It's good practice in machine learning to normalize all your data, independent data between 0 and 1. And then my Y data, I use the one-hot encoding method to process that. You'll notice that I haven't modified X like this in the data set because I still, when I grab instances from the data set, I want to have them as a 28 by 28 image so I can plot them, for example. We're actually going to do this inside the actual neural network. So the network is going to be the thing that takes in a 28 by 28 image and transforms it into a 784 vector. So that's not done in the data set here. You also need to define a length function. So this says how many images I have. You can define this however you want. This is just the shape of X. So here, for example, this is a shape, and I take the 0th value. So there's 60,000 images. So this will give 60,000 values. And you also have to define a get item value. So there are 60,000 different things. And if I want like index, so that's the index of what of the 60,000 I'm taking, it just will return self.x at that index. So self.x is my independent data or the image, and self.y at that index as well. So I've defined my data set object. The initialization only takes in a file path. And so I define my train data set. So that's what I'm going to use to train my model. And then also a test data set, which the model doesn't see during training. So I'm fitting on part of my data, and I'm seeing how well does that generalize to data that the model hasn't seen. So we're going to test to make sure the model isn't overfitting. And I'll explain that a little more in depth in a bit. So I have my train data set and my test data set. There's two different files. There's the training data and the testing data. So I load them. And because I've defined a length and get item of this class in Python, that allows me to use other functions. So for example, this train data set, which I've loaded, I can use the length function of Python. It's going to call this, and it will give me this value. So it says there's 60,000 different images. And the get item allows me to index my data set. So here, for example, I'm taking the first thing, which is going to give me my first image and my first label. So here I give train data set 0. It gives me my first image like this. And it will give me my first label in the one-hot encoded form. So this is a 0, 1, 2, 3, 4. This is a 5, right? And so this is my image and my label. And then the other beautiful thing is you can use slicing. So I can get multiple X's and multiple Y's using slicing. So here I want the 0 to the 4th value. And I can look at my X's and Y's, and X's will be, if I look at the shape of this, it has given me 4 28 by 28 images. And my Y's, it's given me 4 one-hot encoded vectors where the vector tells me what label I'm looking at. So a 4 or 5 or a 6. Then there's the data loader object, which comes sort of along with the data set object in PyTorch. And so what you do is you put data set objects inside data loaders, and data loaders, the reason why you have them even as a concept is because they're useful for training. And in training, you specify something known as a batch size. And so I'll explain that in a bit. But each iteration through the data loader will yield a tensor where the first dimension is equal to the batch size. So what does that mean? Well, let's actually look at it. So here I pass in my training data set, and I specify a batch size of 5. So now I have my train data loader. And you have no idea how this is any different than a data set currently, but I'll show you how it is. So if you iterate through your data loader, a data loader is something that can be iterated through, right? And so here I'm going to iterate through my data loader, and I'm going to print the shape of X, so that's the first thing that is taken out of my data loader, and the shape of Y, so that's the next thing that's taken out of my data loader. And you can see that it's a batch size of 5, that's how I specified it. So it gives me 5 28 by 28 images and 5 one-hot encoded vectors of my labels. And you'll note that, remember, I have 60,000 different images and my batch size is 5, right? And so my data loader, it gives things in batch sizes of 5. So if I divide 60,000 by 5, that's the number of things that my data loader can give, right? It will give 5 by 28 by 28, the first 5 images, then the next 5, then the next 5, and it can do that 12,000 times because there's 12,000 different batches of 5. This is the terminology of machine learning here. There's my full data set, my batches, which are size 5. The batches are specified in the data loader object of PyTorch. And so if I take the length of the data loader, well, it only thinks of things in terms of batches. So there's going to be 12,000 batches of size 5, and that gives me 60,000 images. If I take the length of my data loader, I get 12,000 different things inside my data loader. We'll be using the cross entropy loss function in this video to train the model. I went over that in depth in this video here. I'll put a link in the description above as well. And so here I'm defining my loss function as the cross entropy loss function. I encourage you, if you haven't seen that video or you don't know what the cross entropy loss is, pause this video, go to the other video, watch it in its entirety, because the cross entropy loss function is crucial for machine learning, but it's often misunderstood, or you use it and you don't really know what's going on. So now we'll define our neural network. So our neural network is defined the same way as we defined it in previous videos. And the first thing this network is going to do when it takes in an input, so a 28 by 28 image, is it's going to squeeze that into a -1. So it will take in, for example, a batch size of 5. So it'll be 5 by 28 by 28. And it's going to say, I'm going to maintain the batch size, so it's still 5 in the batch. And I'm going to convert the last 28 by 28 into 784. So it turns a 5 by 28 by 28 image into an image of size 5 by 784. So it's turning each of my images into a 784 length vector. Then it feeds it into the first matrix, the second, the third, like we did in the previous video. And finally, it returns X. So here I can define my neural network, and I can actually look at the network predictions. So I have my X's. So my X's is the first 4 elements of my data set. So it's 4 28 by 28 images. And if I use .view -128 squared, it will keep the size 4 here, and it will turn these last two into 784. And I can do this, and it now gives me something like this. And if I look at the shape, it's now 4 by 784. So that's what the first line is doing here. And I can feed these X's just as their image form like this. This is the shape of them into my function f. So it will take all of these and it will put them through the function. And it gives me something that looks like this. And if I look at the shape here, it's 4 by 10. So it takes in 4 images, 28 by 28, and returns 4 different probability mass functions. So it just returns a bunch of random values right now because the function hasn't been optimized yet. And this is what they should eventually be equal to, right? These numbers should eventually be tuned such that they eventually give these values right here. And we do that using stochastic gradient descent and the loss function that we define. So the loss function is, like I said, the cross entropy loss function. And I can feed in the prediction of my network, which gives me my y hat or my predictions up here. And I can feed in also this. And I can use this loss function to compare, well, how similar is this to this? And right now it's not very similar at all. But I can compute this loss function. I compute the cross entropy between these vectors. And I get a value of 2.35555. And as I use stochastic gradient descent, this value will get smaller and smaller. And that means that my prediction here is closer to this. So what you do is you adjust the weights of the neural network f such that L, the loss function, the cross entropy between these vectors, is as small as possible. And we do this below. So here I define my training loop for optimizing this. And let's go through it slowly. So what this train function will do is it'll take in my data loader, so my train data loader above, and it will take in my network, f. And I'm going to train it for 20 epochs. My optimizer is the stochastic gradient descent optimizer. It takes in the parameters of my neural network, f. And my loss function is the cross entropy loss function. So this is used for optimization. And then I'm going to train the model above. And so I have my losses. This will be my cross entropy between the vectors at each iteration. and the corresponding epoch that corresponds to these losses. So then I make a for loop. So remember that each epoch should go through the entire data set once. So I look at all 60,000 images and I'm training my network. I'm optimizing all the parameters for all 60,000. Then I do it again and again, and I do it 20 times. So I'm going to optimize by going through my entire data set 20 times. So I'm going to loop 20 times like this. And I'm going to print the epoch number so that you know which one it is. Then n is the length of my data loader. So there's going to be 12,000 different batches of my 60,000 image. So n is just going to be 12,000 here. And I'm going to use that in a clever way below. Then I'm going to loop through my data loader. And so this is going to loop 12,000 times because I'm going to have 12,000 batches of size 5. So I train my network exactly the same way I did in my previous videos. I compute the loss function, I use backpropagation, and I use the optimizer to adjust the parameters of my model. Then what I do is I store the training data. So my epoch number is going to be the epoch above. So it's either going to be the first, second, third, fourth. That's just my epoch. And then I over n gives me how far I am into the data set. Remember that this is going to loop 12,000 times and n is equal to 12,000. So I divided by n is always going to be less than 1. And at the beginning of my epoch, it's going to be really small. And at the end, I will get closer and closer and closer to n. And the epoch that I'm going to append is basically going to be like 1. Then the next loop over the data loader, it's going to be like 1.001. And it will give me the loss for that particular batch when I compute it in my training procedure. So it will store all that information in these two lists, and I'll return arrays of the epochs and losses. And the function itself that I feed into it, all the parameters are going to be adjusted within the training function. So we can run the cell. This gives me my training function, and let's actually train the model for 20 epochs. So this will give me my epoch data and the corresponding loss data. As you'll see, it takes a little while to train. I think it's about like 10 seconds per epoch. So I'll be back in a few minutes. Okay, so the training has completed. It took about 2 or 3 minutes. I've trained 20 epochs. The model parameters have been adjusted. Remember that there's 12,000 batches per epoch. Remember, each epoch is 60,000 images, and I'm feeding in batch size of 5. So it's going to do 12,000 updates to the model per epoch, and I've trained for 20 epochs. So it's done 20 times 12,000, whatever number that is, adjustments to the model, parameter tunes to my original model. And so let's actually plot the loss function for each batch. And so I'll do that here. And you can see that it looks pretty noisy. The reason for that is I'm plotting as a function of epoch number here. So between 0 and 1, the first epoch, there's 12,000 different losses that have been computed. And so it's very noisy here, right? You can't really tell what's going on, but you can see that it's kind of getting smaller, but there's really a better way of doing this. So remember that like I said, each data point corresponds to the loss evaluated on a batch of 5 images, and an entire epoch is 60,000 images. So there's 12,000 data points between here and 1, for example. What we can do is we can average the loss across each epoch to get the average loss for each epoch, all 60,000 images. Since there are 20 total epochs that I trained for, what we'll do is we'll split these arrays above. Remember that, for example, loss data, if I look at the length of this, it's length 240,000. So what I'm going to do is I'm going to split this array into 20 equal portions. That will give me 20 epochs here. And I'm going to take the average over each of those 20 equal portions. The way to do that is to first reshape the array like this. So if I reshape it, my new shape becomes 20 by 12,000 here. So I've split it into 20 different portions. Each of these has 12,000 different data points. Remember that that's how many batches of 5 there's going to be in all 60,000 data points. And then what I can do is I can take the mean of this array. And I take the mean across all 12,000 data points. That's my first axis. So I take the mean like this, and it will give me 20 different losses here. I do that for my loss data and my epoch data. Of course, this gives me like 0.5, 1.5, 2.5, because the epochs, of course, just are linear between 0 and 1. So I get my averaged data for my loss, and I can plot them like this. And so this gives me my average cross entropy across all 60,000 images in each epoch. And you can see that as I train, the cross entropy gets smaller and smaller, which means that the predictions of my network and the true labels of the images are getting closer and closer together. So let's actually look at a sample image label. So here I'm taking my train data set. Remember, train data set looks like this. I can take the first element of my train data set. It gives me the image and the corresponding label. If I want the label, of course, this is a tuple of my image comes first and then my label comes second. So I take the index 1 here, and that will give me my label. So this says that this is a 0, 1, 2, 3, 4, 5. This image is a 5. And that's my Y sample here. And it, sure enough, is the same value. And I can look at my sample prediction. So for that, I need my X sample. Here, I'm just looking at a sample data point. That's my train data set 0, 0, because I want my image. I feed this into my neural network, and it will predict a sample prediction, a sample probability mass function. Of course, as you'll see here, it's not normalized. This is not an actual probability mass function. The cross entropy function takes care of that. The cross entropy function will actually normalize this vector using a sigmoid function. That's not really important here if it's not normalized. The point is that the number that is the largest here corresponds to what the prediction is. So for example, this is 0, 1, 2, 3, 4, 5. And the largest value here is also the 5. So it's saying the most likely class that this belongs to is this number right here of my sample. And if I want to see what actual value that is, I just take the argument maximum here. So it will tell me that this is 0, 1, 2, 3, 4, 5, the 5th class. And that's what the argmax function does. It says 5. So that's the index 5. And it just so happens here that the index corresponds to what the actual image label is. So a 0 is a 0, an actual drawn 0. Index 1 is the image corresponding to a 1. And so I have my label 5 here. And sure enough, if I show this image, it is indeed the number 5 that has been drawn. So my network is able to predict that it was a 5. So now we'll look at a few more predictions. So for example, here's 2,000 different images. And I'll just move this into the cell above, actually. So this will give me 2,000 images and 2,000 labels. And if I look at the shape of these, 2,000 images, 2,000 labels. 2,000 images of size 28 by 28, 2,000 labels where they're each like that vector of length 10 where, you know, one of them is a 1 and all the rest of them are 0. That's how I get my labels. And if I want to take my network, I can take my network and plug in all these images. I get my f of x's. And if I look at the shape of this, they correspond to the same shape as the y's. And if I want the actual image label, I'm going to take the argument maximum for this first dimension here. So it's going to say what index is the maximum across this first dimension. And if I go like that, so I'm taking argmax across all 10 of these values here. And it says that, well, the first one is a 5, then it's a 0, then a 4. So these indexes also correspond to the image label, like the actual digit that's been drawn here. So that's how I get my predicted labels. And I take f of x's and then the argmax x equals 1, or axis equals 1. And I can plot a bunch of these. So this is just a for loop that creates an axis. There's 10 rows by 4 columns. So it's a fairly big plot here. And I'm just going to loop through all 40 different images and plot them on a different subplot. And I'll also give them the label of the predicted digit from the y-hats that I have here. So I run this cell to create some plots. It takes a little bit to load. And you can see the predicted digit and the actual digit. And the network is doing a very good job of predicting all these digits. In fact, these might all be correct. Now, those predicted digits were predicted on the training set. So this is all the digits that I fed into the network, and it sort of learned to adjust its parameters based on these images. But I also want to test the generalizability of this model. I want to feed it maybe a new image. You know, maybe it can do it on these images that it's already seen, but can it take in a new image and also make a perfect prediction? Well, for this, we have to evaluate our model on a test data set that the model hasn't seen during training. So here we have data that the model hasn't seen during training. That's my test set. I'll take the first 2,000 images and labels here. I do the same thing as above, and I'll plot 40 predictions. And going through, remember, these are images that the model has not seen during training. And sure enough, it's making very good predictions on these images. In fact, I think these are all correct too. There's only a few, I looked through this, there's only a few that it actually doesn't predict correctly. Even things like this, that being a 4 is very strange. And not all of them are written so nicely. And so the model does a very good job of being trained here. And just to sort of finish off this video, I want to really reiterate about how simple the structure of this network is. All I did was a few matrix transformations followed by a few activation functions, and it's able to take something as complicated as an image of a number and predict what number that is. So these neural networks, although they consist of very simple model architectures, are able to do very powerful predictive things. Anyways, if you enjoyed this video, please be sure to like and subscribe. Join the Discord server. There's going to be more tutorial series in the future, so look forward to it.